Calculus people. Good morning to you.
Morning, Doug.
Thank you for saying so. It is a good morning. Let's see. Let's get this computer to wake up. So from the syllabus, we have a little more time with 8.3 today, just taking the integral of trig equations. If you went in there yesterday to look at your assignment, you saw that there was more complicated questions than what I gave. And so I want to give you a little bit of time just kind of wading into that concept so that you think, oh, okay, I got that now. Let's see. Let's do that with this question. So 8.3 continued. So we looked yesterday at the integral of sine squared. Let's look at the integral of sine cubed. And again, what I'm overall interested in, I mean, I want you to get your assignment questions done, absolutely. And I'm going to give you enough help with that specifically today that I think you'll be okay. But I'm more interested in just that you keep observing, if you will, the creativity involved in this process. And so watch this. And I'm gonna, I don't know, a little bit, maybe a little bit today, speed up to get through a few more examples. We spent our time kind of doing the mathematician's lament approach yesterday and playing with things. And by the way, I was very tempted to do the same thing today, like play some more. So we'll strike a balance. But let me show you a really creative way out of this mess. And it's totally different. Like, so we said that sine squared could be rewritten as 1 minus cosine of 2 theta over 2. And then we also saw that integration by parts worked, which was totally exciting. And so what about something cubed? Well, so, you know, what choices do I have? Well, I could split it into sine squared and sine maybe, and then try integration by parts. I could let u be equal to the sine of x, or this creative idea. So this time I'm going to show you kind of the fastest way quickly. This creative idea, what if you split it into sine as proposed, and then the sine squared, but rather than substituting and letting u be sine of x or something of that nature, isn't it true that since, as an abbreviation, sine squared plus cosine squared is equal to 1, does it make sense that I could then replace that sine squared of x by subtracting cosine to the other side? I'd have 1 minus cosine squared of x. Now at the outset, that seems like a terrible idea because I'm just making this more complicated. But remember, substitution loves it when one thing that you would like to substitute, its derivative, is sitting over there. So this is kind of a cool trick. So then if I let u, or let's choose a different letter, why does u get all the love? Let w equal the cosine of x, then I could say that dw is equal to negative sine of x. See what I'm saying? The derivative of that, what I substituted, is sitting over there. Dx. Then what do I have now? Well, I've still got that sine of x out front. And now I only have 1 minus u squared, which is nice. But then what happens when I replace that dx? Well, if I divide this sine of x over, then I end up with dw divided by negative sine of x. And so do you see again, this is the classic example of substitution. The thing you're substituting's derivative is in the problem. Oh, look, bam, bam, those are gone. And so all I end up with is, I guess I could, I said u, why was I saying u? It's my own fault for choosing something different. I let W be cosine. So now everything is W. I still have that minus sign that I don't want to lose track of right there. And so I think I'll just turn it around and make it positive W squared and negative 1. Does it make sense? That is an easy integral to take. So the integral of W squared is, of course, W cubed over 3, or 1/3 W cubed. And the integral of 1 is W. Done, except for I just have to throw cosine back in. So it'd be 1/3 cosine of x cubed minus cosine of x. And let's go ahead and throw this plus c in there this time for good measure. So again, isn't that kind of creative? Like, I don't know if I would have thought of that.
I have a question.
Yeah.
Where does that negative go when the dw over negative sine x?
I just distributed it to both of these. That's why the W squared, which was negative, turned into a positive. So it doesn't go away. Now you could have just pulled it out front and that's fine. But I just decided, oh, I can put it in there. You with me?
Yeah, I see where you got that.
Yep.
Yeah, honestly, having, I mean, it doesn't really matter, but having that variable in the front of the squared W just looks nicer or better to me. I don't know why.
Yeah, it's kind of clean. Save me from the, possibility when you put that out front, you might forget it accidentally and so forth. But so that's kind of cool. I mean, that's not obvious. Would you agree with that? That's not obvious. So when you have a cubed equation, sine cubed or cosine cubed, you can always like pull out a squared, and that's really kind of a cool trick. It's when it's to an even power that you're kind of in trouble. So that's kind of neat. Or of course, if you were given a problem where there was already one there. In other words, something like this. Like, what if you had the cosine to the 6th power of x, which is terrifying. That's a big, long, ugly problem. You don't want that. If it was to the 5th, we'd be able to use the same trick we just used, because you can leave one cosine behind. But if that problem wasn't done, and
Well, couldn't you also rewrite it as cosine cubed x times cosine cubed x and still do the same thing? It would just be in 2 parts.
No, because if you did that, you're going to have a cosine for each one of them, or a sine for each one of them, and then you'll have a sine squared. And so there's a creativity to this. That's the thing I want you to understand. Like, you can't, in a sense, get away from that. So this problem right now is terrible. Actually, I think I'll switch this to a sine just so it's different than the last problem. That's terrible unless I come and add this to it. Now all of a sudden it's easy. In other words, the derivative of sine is cosine. It's already sitting there. That problem just got way easier thanks to that cosine being there. In the last problem, I had to put it there myself. So you have a lot of assignment questions that kind of look like this. So let's just kind of play around with this a little bit, give you a bunch of examples. And so if I let, m never gets any love, let m be the sine of x. And again, that's a classic substitution, because do you see the sine of x to the 6th power as chain rule? In other words, junk inside of junk, not junk times junk. That's integration by parts, but junk inside of junk. In other words, I can handle m to the 6th, the integral of m to the 6th is m to the 7 over 7. But I can't handle it when there's both sine and to the 6th power. Well, if I let m be the sine of x, then this problem becomes m to the 6th. Oh, that's totally easy now. The problem is there's some collateral damage from that, because I still have this dx to get rid of, as you know. And so if I take the derivative of m and the derivative of the sine of x, so that I create some dx's to get rid of, then So I'm still stuck with that cosine of x, but then what is dx if I divide both sides by the cosine of x? Again, amazing. Like that problem is almost canned. Like, wow, like, you really made that up nice. So I didn't have to somehow draw, as we did yesterday a little bit, I didn't have to draw a right triangle for this and somehow rewrite cosine because it just canceled out. So we love it when the derivative of what we're substituting is sitting there, because this is what happens. And so this problem is just super easy now. Bam, bam, that's gone. So it really is just the integral of m to the 6th dm. That's super easy integral to take. That's m to the 7th over 7. I'm done, except for now I just put m back in. So that'd be sine of x to the 7th power divided by 7, or times 1/7, and technically plus c. And so, man, throwing that cosine in there made that problem way easier.
So Doug, I'm not super strong on this, and I didn't know right off the bat what to let m be. If I let m be cosine in that situation, I would get dm over sine, right? And then it would make that sine to the 5th, and then we'd be able to do the trick you were talking about.
I don't know. Let's try that really quick. And to Connor's point, Connor said, I'm not really strong at this. Well, do you see? You shouldn't be. And that's part of why I did what I did yesterday. Do you see more options? Again, don't I make this look easy by choosing the correct choice for what to let m be equal to? But teachers will make it look like, oh yeah, look how easy this is. But like, that's not the only choice. Like, how did I know to let m be equal to the sine of x here? Well, it's because I have a lot of experience at it. So you should not think that's obvious. And so let's just try Connor's idea and see if that creates a mess. The thing you have to do is just be careful about the algebra. Like, make sure you really are slowly getting rid of everything that needs to be gotten rid of. What if you let m be the cosine of x instead? Would that also work? Is that a disaster? I don't know is the answer to that question. And let's see, that would mean the derivative of m is equal to the derivative of cosine is negative sine of x, and the derivative of x is the derivative of x. So what does my problem become? Well, I still have the sine of x to the 6th. And I no longer have cosine because I called that m. And then if I replace that dx up there with what this tells me dx is equal to, that'd be dm over negative sine of x. So do you see how, well, one of the signs cancels out, which is what Connor said. He's right. So I guess I could say, and maybe I'll pull the negative out front since I don't have any place to disappear it. This would be sine of x to the 5th because I canceled one of them, but there's still an m and there's still a dm. Great. So I'm happy with everything except for that stupid x. Like, there's still an x there. So you see I didn't cancel out. So the way I did it was, well, if you will, much easier. But again, from your perspective, that should almost be a flip of the coin. Like, oh, darn, I chose the wrong one. Does that mean this doesn't work? Well, not necessarily, because I have to draw a picture of this. So we said that a little bit yesterday. If you're taking the cosine of it, it's an angle. So there's angle x. Cosine is m over 1, adjacent over hypotenuse, m over 1. And we needed to know what's the sine of that angle. Well, sine is opposite over hypotenuse. And so this opposite side over here, according to Pythagorean theorem, would be 1 minus m squared. And so sine of x is actually equal to the square root of 1 minus m squared. Mission accomplished. Now I got it. It's negative the square root of 1 minus m squared. So that's the square root of 1 minus m squared. But then it's raised to the 5th power. So you know your algebra, I hope. So that would be that. Again, mission accomplished. I got it all into m's, but that's pretty darn ugly still. You're not done. You see what I'm saying? So will this not work? My guess is it probably won't, or at least it's going to take a bunch more substitutions, but I have to keep going. I did successfully get it into m, but I can't take that integral now. And I can't distribute the m inside because it's the 1 minus m squared is under a square root sign. So I can't just distribute m inside. I got two different terms. Now I'm thinking, I wonder if I should do integration by parts. I wonder if I should let u be equal to 1 minus m squared. And so it's kind of like it's on. I don't know. I'm not sure. So you just got to expect that when you're just learning this. In a sense, I made the correct choice. I made the easy choice. Maybe I didn't know it, but I made the easy choice. Now, what I said before is really important, the intuition of this. Look, the thing I chose to let m be equal to its derivative is sitting right there. Like, look for that. Now, because these are book assignments, you're typically not going to end up in that green mess. Like the problems are going to be carefully enough handed to you that you're not going to end up in that kind of a mess. Let's look at some other just creative things that you wouldn't think about. Like, what if it was like the integral of tangent squared? Do you have three ideas here? Again, I don't know if we'll probably won't follow any of these today, but what would you try? What are some choices? What might you try?
You can turn it into sine over cosine.
Yeah, maybe you substitute it into sine over cosine. Now that's substitution again, but it's just not changing a letter. So maybe that would be promising. That's worth looking at. Good idea. I didn't think of that. What else?
Well, it could also equal secant minus 1, but I don't know if that would help us really.
Yeah, another similar substitution. Isn't tangent squared equal to secant squared minus 1? What's another idea? Should have more ideas from yesterday.
I mean, could we just let u equal tangent?
Yeah. Every one of you should have told me that just now. That's not a good sign from things that we did yesterday. It's junk inside of junk. So simplifying it by letting u equal to tangent x, then in a sense that should have been your first answer. That's what substitution is.
Sorry, but I feel like simplifying it that far might just put us in a bigger mess.
Yeah, and
because
that's the whole point.
And I'm just, maybe you could also do integration by parts, 1 times tangent squared x. Maybe that will help.
Yeah.
That also seems like it would also put us in a big mess. Instead, I'm thinking number 2 would be the best option.
Yeah, or even to what your point, Eve, rewriting it as tangent times tangent. Hey, look, 2 things multiplied together. So I could write it like that and then try integration by parts. And so this is my point. You should, to me, you're not really understanding your tools, the tools you have. You have integration by parts and you have substitution. That's the only tools there are. What do we do? This is a substitution. This is a substitution. This is a substitution. This is integration by parts. Like those need to occur to you. And to Eve's point, yeah, some of these are going to be a mess and they may not work at all. Like they'll take you out in the woods. Is there a Jimmy John's around here? And all you see is trees and dirt and a dirt road. It's like, man, I'm gone. I'm out there somewhere. I hope that part of you sees that as fun. I mean, you got other things to do and you only have so much time and, you know, this can make you mad and that's okay too. I'm out in the forest, but it's like, see it as an adventure to the extent that you can. Now, there is one of these that is uber easy. It was a brilliant idea. Does anybody see it?
Is it
Well,
number 2?
I think it's the first one, yeah.
Notice you're not sure. The easiest one is this one. Does anybody see
Well-
why?
Well, because isn't the derivative of secant squared x tangent x?
Yeah. Wasn't there the derivative of something was secant squared? The derivative of tangent was secant squared. So if you are lucky enough to write that one, and again, your gut reaction to that should have been that's worse because at least tangent is SOHCAHTOA and secant is not. And so I could see you have written number 2 off as like, forget that. But the derivative of tangent was secant squared. So the integral of secant squared is tangent and the integral of 1 is x, you're done. So that's the problem with these questions. Like, where's Jimmy John's? It's right behind you. Turn around. You're there.
Yeah, it's, I don't know, I'm starting to feel like, it's not really the one that looks the easiest, but if you actually like try to potentially plan maybe 1 or 2 steps ahead by looking at what that derivative could potentially be, it's helpful. It's like playing a, like a chess move or something.
Yeah, and that's exactly what this is like. I don't have the patience for chess, but it's like if you're going to win at chess, you can't just think, I like queens, I'm going to move that one. Like you got to think ramifications down the road. And of course, the reason I don't like chess is because I haven't practiced enough to know what those ramifications are, right? That's why I don't like it. Well, it's the same thing here. Like you're just learning this. I just showed you this yesterday. You didn't even know this existed until yesterday. So, how are you going to have the intuition to choose the right one? So in my opinion, as a teacher, it's a total mistake for me to do this problem like I did here in purple and just say, look, let m be sine of x, as though that's the only choice there is and it's totally obvious and you could do nothing else. I think it's really important personally to list the possibilities and stare in them a little bit. And if you have the time and you find this exciting or you find this interesting, to actually run down those roads a little bit and see whether it's going to put you in the weeds a little bit. And that's why I took the time to retry this one per Connor's suggestion by letting m be cosine, and notice it indeed put us out in the forest, like it put us in the weeds. Does that mean that doesn't work? No, but it just might mean it's the long way there, but it also might mean it doesn't work. Now, because you're being given book problems, there will be a relatively simple approach. That doesn't mean easy, but they're not giving you problems that are going to take you way out in the weeds.
I
So
like going.
you just need practice.
I was gonna say I like going way out in the weeds. That's why all my shoes are messed up.
Yeah, it's kind of fun if you got the time,
If I do a lot of mushroom hunting, and I'm not shy of the bushes. Well, not so much since I've been coming to school, but yeah.
So let me show you one thing. I don't like mushroom hunting because I haven't practiced enough, and when I go out there, I never find any. We need to talk.
Took honestly, it was like joining Facebook groups that are like ID groups, and it just paying attention to those and buying a couple of books. And it did take a lot of not finding anything before I actually got relatively decent at it.
And that's kind of the point of this. Like, I got news for you. There's no shortcuts to anything in life. Like, if you just think you're going to be a natural mushroom hunter, you're going to go out there and just be natural at it. That's very unusual when that's the case. You just have to get out there and put time. I heard a guy talking the other day about people learning things, and he was talking about kids learning to walk, and it's like nobody talks to kids and tells them how to learn to walk. It's like they just fall, and the person said they did a study, kids fall 70 times an hour, which is more than once a minute. They stand up and they fall, so they're falling once a minute, yet they just seem to have this innate desire to keep at it, and then pretty soon they're experts at walking and nobody taught them anything. There's no substitute for just spending time.
Young kids also don't have a sense of failure.
That is
They just do what they do. They don't feel the immediate
true.
emotion of failure.
That's true. And if some other kid near them is walking before them, they're not ashamed, like they don't have a sense of self-awareness. So it's totally true.
Yeah, until society programs it into them to, you know, be ashamed when they really shouldn't.
Very true. Let's see, I'm hoping this is in here, but I didn't look ahead of time, so I guess I don't know. That's disappointing.
But I guess on that note, I have tried over 20 different mushrooms I've harvested from the wild now, and I started 10 years ago with just morels. So
Cool. Yeah. From my
some aren't.
there is no such thing as a morel. It's like Bigfoot. I've only tried twice. I've looked for mushrooms twice. I spent 15 minutes each time and then gave up.
Yeah, I've found every kind of morel for the most part. There's one I have not found, and I think I might have found it. I just didn't realize it at the time because I didn't realize there was different species of them. But
Can I make a suggestion for a problem to do?
Yeah,
Unless you're still looking for your thing.
I gave up because it's not there.
I was doing the homework last night and I
Mhm.
found one of the problems particularly tricky. I figured it out,
Mhm.
but I think it would be important for me to do it again because it's just kind of one of those problems you don't see very often.
Yeah.
I think it's it was problem number 3. It says back substitute to write your solution in terms of x.
Which is what we did here. In other words, we got done here and we got m to the 7th over 7 and we back substituted to put the x back in it again because there never was an m there. So it's kind of idiotic to write the answer as m to the 7th over 7. So we put the x back into it. So that's just
Oh.
language.
See, that took me forever to figure out and I don't know why.
Well, that's one of the things that's hard about math is the language of it versus just the logic of what to do.
Yeah.
So that's not weird. So I got to be a little careful when I make problems up to not make up something that you can't do, if you will. Let me see if this is in the book somewhere. Oh yeah. So you might consider looking at this at the back of your book because I did want to look at something like this because there's some cool simplifications in your book that weren't in that trig table that I posted, which is, if you will, a little disappointing. But before we do that, let's consider a problem like we just did, except for let's just take it up a notch. What about the integral of tangent cubed of x? So there's a part of me, and I haven't prepared this example, which I think is important that I don't, but there's a part of me that kind of wants to start like we did with sine, which is where I'd say I'll split it into tangent of x times the tangent squared of x, and then I'll replace that with secant squared minus 1. And I'm kind of wondering, is that good? So that seems to be worth trying. Again, I could split it into sines and cosines because I feel a little more comfortable with those. So I don't know, let's just play with that a little bit. Let's try that rather than, list maybe 5 ideas. The other option would be to let u be tangent of x. That's an option too, but let's just see if this goes anywhere. So now I kind of have, the problem is that one option I just chose. Now I'm also seeing other options, like I could try integration by parts. I could try letting u be tangent of x. In a sense, what we did with the trig problem was, let's just try what we did with the trig problem and see if that universal option fits. If I let u be equal to the secant of x, see, the problem is the derivative of u, the derivative of secant is secant tangent. Secant of x, tangent of x. So I'm looking at that thinking, wow, I don't see that that's going to cancel things out. You see how it's not looking so good right now? Again, I'm not going to give up just yet, but I'm thinking, I don't know. Is that going to work? Well, let's go see what we got. Let's not give up. Let's just see. Well, I had the integral of tangent of x times, and the whole reason I chose that substitution is now because instead of being times secant squared x minus 1, it's times u squared minus 1, which is good, but I still have that tangent. I'm not really happy about that. And then to get rid of the dx that's over here, I have to divide secant tangent to the other side. So this would be du over secant of x tangent of x. What do you think?
It works, doesn't it? Because you could do the tangents cancel, and then I guess you could plug in another u for the extra secant x.
Yeah, notice, actually, this is looking promising after all. Do you agree with that? Good eye. In other words, hey, the tangents did cancel. And miraculously, I'm not unhappy about secant being left behind because don't I have a name for secant? So, whoa, dude. So again, success. But the question is that easy? Can I take that integral? Is that easy or hard? April's thumbs up on that. You may have forgotten this, but this is easy.
Could you separate the fractions, cancel out the u, and then do natural log of u?
Exactly. We don't like plus and minus signs on the bottom, but we don't care if there's plus and minus signs on the top, because can't I split this into u squared over u minus 1 over u? In other words, unadd the fractions together, so that this becomes the integral of u minus 1 over u. We love minus signs because I can do those separately. The integral of u is u squared over 2. The integral of 1 over u is natural log of u. Mission accomplished. Now, in the language of the book, whatever Eve said, reverse substitute or whatever, u is secant of x. Just put that back in. So 1/2 secant squared of x, since u is squared, minus the natural log of u, which is the secant of x. Bam. So the first thing I tried actually worked, and again, no kidding, I didn't think that was going to work. I didn't think that was going to make sense. I was wondering in my head if I shouldn't tell me if you see the logic in this statement. I was wondering if I shouldn't let u be equal to the tangent of x. Can anybody tell me why I was thinking that might have been a good idea? what's the derivative of tangent of x?
Secant squared x.
Secant squared x.
Secant squared x. And the reason I thought that might be a good idea is because I have a secant squared x. That was on my mind when I was doing this. So even the fact that I chose to split it up like that, I had a second choice as to what to substitute. And then I also didn't try integration by parts. And so in my opinion, in my, even with the experience I have, I just got really lucky. Like the first thing I tried actually worked. Now, is it the easiest thing? I don't know. Is there an easier way? That wasn't too hard. I didn't have to do multiple substitutions. So there, my guess, my intuition is that was actually probably the easiest way. Miraculous. I'm curious if the integral of tangent cubed is in the integral table. I think it is, and I want to look and see if we got it right. Did we get it right? I thought we had a,
Yeah, it says we have a natural log of secant x.
didn't we have secant? So the question is, did we make a mistake or is there other ways to write it? Remember with trig, there's always other ways to write things. The other part was the same, 1/2 secant squared. By the way, remember secant squared, anytime you see a squared equation, you should think, oh, Pythagorean theorem. Secant squared is tangent squared plus 1. So there was a part of me that expected that secant squared to be replaced with tangent squared plus 1. I would be inclined to do that because I don't have a secant button in my calculator. Remember, if I was using this to evaluate from, say, 3 to 1, does it make sense I'd have to put 3 in there and take the secant of 3? And I don't know what that is. So there's a part of me that says, I don't like this answer. It's a dumb answer. If they're not wrong and cosine could go here instead of secant, I really like that answer. I think that makes all kinds of sense. Let's just go play with that for a second. Anybody see how they might have got that?
It's a negative in ours and not in theirs.
Yeah, we have a negative in front of natural log and they had a positive.
I think they just put in 1 over cosine of x for starters.
You are not wrong. So that's weird because they don't have cosine. We have 1 over cosine. But remember this fact about logarithms that you learned at one time, but maybe you forgot. Would you agree that 1 over cosine is the same as cosine to the -1 power? Can't you move it to the top and say -1? By the way, a little side note, -1, inverse cosine and cosine to the -1 look identical, but they don't mean the same thing, which is really annoying. And what's true about logarithms when they have a power up here? If that was like an 8 or something like that, can't that come down front? Oh, that's what they did then. They brought it down front. Hey, that's a way better answer. I totally agree with them. Does it mean our answer is wrong? No, not at all. It's right. Why do we keep doing that?
Do you see any reason why they wouldn't have just replaced that secant squared with a cosine as well?
I do not at all see why they did that. Am I right about this? Is it secant squared is tangent squared plus 1? Is that true?
Yes.
As I said, that's the only buttons I have on my calculator, sine, cosine, and tangent. So I'm very surprised that this was not the answer in the table. Now, I think the reason was probably it's longer, like it's a little bit bigger than it was before. But that's terrible, because now if I want to evaluate this thing from 3 to 1, I got buttons, right? I got tangent button and a cosine button. And so the whole point of this is to use it for something. So I like that answer better. This one is okay. This one, in my opinion, is the best. But do you see how good you got to be at trig, and in this case, even the properties of logarithms? Like it sort of punishes you if you don't know everything you've ever learned about algebra. So let's do this. Let's not talk about 8.3 anymore. However, we'll start talking about 8.4. However, you should do the 8.3 assignment tonight so that you come tomorrow with ones that did not work easily for you. You should not just be able to sit down with that, whatever, 12 question assignment and just go buzz all through it and get all the answers right. That should not happen. You should have at least half of them, if not every single one of them, where you don't choose the easiest substitution. And so I'm not going to volunteer it, but if we start class tomorrow and you say, hey, I really had trouble with number 7, then I'm going to do it with you. I might change it. I might just do it. I might just do the problem for you. If you don't start it tonight and I do the problem for you, then you will learn nothing. Like, you have to struggle some in order for, my advice to help. But again, as a teacher, I'm very sympathetic about this, because you could spend 12 hours on this assignment with the lack of intuition that you have about this right now, having not practiced that much. Like I could spend 12 hours looking for morels and never find any, and think something's wrong with me. No, you just haven't practiced enough. You haven't had any advice. So if you go work it a little bit and then I come back tomorrow and give you some advice about it, whatever I say tomorrow will sink into you way more than me doing random problems right now. Do you understand that? I do want to say one more thing that might come into play. Let's see, it's not a page, but in the back of your book, you have a table of integrals that has some power reducing formulas. Unfortunately, that sheet that I found online did not have them. That's what I was looking for a minute ago. Power reducing, which I don't think I'm going to go into. And I'm just going to write one of them down for you. This is the last couple of pages in your book. Let's see, this is number 51, and it's for cosine. And it says, if you were sitting here with the integral of the cosine of something to a gnarly power, like 6, and unlike my problem before, there's no sine sitting out here, which would suddenly make that an easy problem. And all you have is that. That's not good. And so there's a power reducing formula. Now in the formula 51, it says that it says that 6 is an n. In other words, they're actually writing a formula for you. Maybe I'll go ahead and do that. Instead of calling it 6, I'll call it n. And they tell me right there that you can just rewrite this as this. So I want you to look carefully at this answer as 1 over n times, and notice I don't have it memorized. I'm staring at the book note, times the sine of x, plus n minus 1 over n times the integral of the cosine, not of n now, but of 2 less than n. In other words, if that was a 6, and I want to write that example down there really quick just so that you can soak this in a little bit better. If I said this was to the 6th power and you wanted to work that problem and you went, oh my God, that's just a lot of exponents. then this is saying it's 1 over 6 times the cosine of x, 1 less power, so that'd be to the 5th. And then there's a sine of x, and then it's plus 6 minus 1, which is 5 over 6. And then it's now the integral of cosine to the 4th, like you just made it better. Can anybody recognize what produced this? Do you recognize what you're looking at right there? You should. What is that? How'd they do that? I don't even, how did, what, we only have two methods, substitution, integration by parts. What does that look like they did there?
Integration by parts.
Yeah, do you see it? Doesn't it look like integration by parts? So we could make that ourselves. I'm not going to take the time to do it, but notice they just made a simpler problem out of it. The main idea here is I'm staring at the integral of cosine of x to the 6th, and I'm like, I don't know what to do with that. And so let's just rewrite it as the integral of cosine to the 4th. Does it make sense I could do it again? If I did it one more time, cosine of 4th would go down to cosine squared. And then I could solve it because cosine squared is equal to 1 minus the sine of 2x over 2 or something like that, like we did sine squared the other day. Now, to me, this represents like a problem I don't want to give. I don't want to put it on a test. It's too time consuming. But remember, I don't care how ugly this is because I don't have to do anything to it. I don't have to take the integral of that. So who cares how ugly that is? I wonder how they split that up. I'll just leave you for this to think about it. Like to do integration by parts, did they make that cosine cubed, cosine cubed? Is that how they split it up? Or did they split it up as like cosine squared, cosine to the 4th? Or did they split it up as just cosine times cosine to the 5th? I wonder which one of those produced that. I guess that's the only choices. But that's not hard. I would encourage you to go try to produce that and be like, oh yeah, as complicated as that looks, that's just integration by parts. Part of me says, I don't need that formula then. But please don't give me, you know, the integral of cosine to the 6th. I don't want to have to do that by hand. That's just terrifying. So if I had to guess, and I do, I would say you're, I don't know, 75% prepared to do the 8.3 assignment. I'd say you're 100% prepared in the sense that I showed you how to be creative and try things. But in terms of just sitting down and kind of going through it fairly, I don't want to say easily, but just fairly comfortably, I would say 75%. You don't have the intuition yet. Okay. Now, fortunately, this is not entirely a new topic, 8.4, and we have the rest of tomorrow to look at it as well. Let's see, since I have the book in front of me, what the heck is this? Last section was titled trig integrals. This section I think is called trig substitution. Yeah, this is trig substitutions. And what this amounts to is making substitutions using trig equations that are very surprising. And we've already, I don't know, hinted at this maybe a little bit. But let me just show you some examples and get you kind of thinking about this. And so this overlaps. This is very similar to what we've been doing, fortunately. It has a very similar sort of a feel. Let's say you have the integral of, I don't know, 5 over x squared plus 16. Would you agree, think very carefully with me about this, if I had thrown an x up there, this problem would have been much easier? We don't like the plus sign on the bottom. That's not good. And so therefore my gut instinct is to let u be x squared plus 16. So why are we really happy that it's not just a 5 up there, but there's a 5x?
Because those x's would cancel.
Yeah, when I take the derivative of x squared, I'm going to get an x, and that x will cancel. That's how substitution works. That's a pattern we've been seeing that I want you to see. That would work great. Can you see that that is not going to work if that x is not there? Now, again, when I say it doesn't work, what do I mean by that? Well, let's proceed. du, that's the only substitution I can think to make. Do you understand what I mean by that? I mean, maybe u is x squared, but remember, I don't like plus signs down there. So that's the only thing I can think to do, is to let u be equal to x squared plus 16. So that means du equals 2x dx. And so, okay, great. What do we got? Yeah, 5 over u. I love it. Sweet. That looks great. I can do this, except for, unfortunately, dx is equal to du over 2x. Dang it. There's no x up there to cancel out. So notice this just tiny change. And back when you were learning substitution, the book and I were very careful not to give you anything like this. Now, does this not work? Well, the answer is, yeah, it works. I mean, can't you go on with this statement up here? Since the x didn't cancel out, so what? Go on and solve this for x. If I subtracted 16 from both sides and then I took the square root, isn't that what x is equal to? Great. So continue. You're not done. So let's see. You have 5 and a 2. I'm taking the 5 halves outside, and I have 1 now over u, and there's also an x down there, which we're now replacing with u minus 16 du. Mission accomplished. Do you agree? Success. Sweet. But that's still hard. You understand that? And as a matter of fact, it actually looks harder. It looks worse. Still hard. Perhaps worse. And that's the only substitution I can even think to make. Do you agree with that? When I'm serious when I say that. I can't think what else I would choose for this. Now, just for a second, I want to show you something I haven't showed you much before, but I want to show you that this actually worked. So let's make a definite integral out of this. Let's go to this. Let's go to the integral of 5 over x squared plus 16. So I'm going to go into Desmos. And I'm going to say, I'm just checking my work here. I just want to remind you that you can do this. This is something you should know, but let's just do it again. We haven't done much of this lately. So we had 5 divided by x squared plus 16. Let's see, what mode am I in? Radians. That's a pretty flat looking graph. So notice the graph exists everywhere. So what I was reluctant to do is to say, let's find the area under the curve from something to something. So let's see, for no good reason, I'm going to find the area from, I don't know, let's say 1 to 5. Before I do that, though, I'm going to make this graph look a little cooler by messing with the y max and minimum. Notice how much more, I don't know, by changing the range, by changing the y max and making it smaller, I sort of blew it up. And so, yeah, let's go from 1 to 5. That looks really cool. So if I go over here and say, what is the integral, since I typed it this way, from 1 to 5 of f of x dx. I cheat. So this problem was not a definite integral. And again, one of the things I like about your graphing calculator is it actually shows the graph. whereas this doesn't show you the area under that curve. And so do you agree? I chose 5 to 1. There was never a 5 to 1 in this problem. But from 5 to 1, it's 0.8138. And what I want to do is just check and see if the blue one is the same thing. Do you understand that? And to make it a little bit easier to type in, I'm going to write it. I don't really want that 5/2 outside, so I'm actually going to put it inside. So it's 5 over 2u square root of u minus 16 du. What's wrong with that picture? Should all know.
Your limits aren't equal.
Yeah, I mean, go back up here. If x is 5, 5 squared is 25 plus 16 is 41, u has to be 41. If x is 1, 1 squared is 1 plus 16 is 17. I'd have to go from 41 to 17 to hopefully get the same exact answer, right? Like this is how I'm checking to make sure I didn't do it wrong. 5 2u, u minus 16. So I think I'm just going to write this one out this time rather than graph it and all of that. No, that's not true. I do need to graph it just so you can see it. It's kind of cool to see that it's like a totally different graph.
Hey, Doug, I apologize. I got to get out of here. I have another class that is at 10 today. They moved it from 11, but I'll catch the rest of this video later.
Sounds good, but it's not as important to this class. Just don't forget that. This is your most important class.
It's electronics. They're both pretty important.
Sounds good, my friend.
Have a good.
Let's see. Do I have the equation right? That doesn't look right because notice the graph doesn't seem to exist. Oh, yeah, it does. Remember, it was from 41 to 17, was it? So really out here, so from 41 to 17 under that green graph is going to be the same exact area. Notice it's a totally different graph. That's kind of cool, isn't it? And yet, if I say, if we didn't, and I don't think I screwed this up, so I'm pretty sure this is going to work. If I say from 17 up to 41, I would like to know the integral of, or the area under the gx curve, dx. Bam, exactly the same answer. Do you see what I mean by success? Well, yesterday and today when I was like, success, I did it. I got it into you. Sweet. Isn't it cool? It's like a totally different graph and yet same exact area. That's how I know I was successful. You can always do that. You can always check your work and make sure that that works. However, as I said, although that's really exciting that we did not screw this up, we did get it into the next, whoa, what happened there? I must have hit the wrong button, crop. We are not out of the woods because we still can't take the blue integral. And as I said, it's worse. And I'm out of ideas. Like I can't even think what else I might do. I can't even think of another choice, another substitution. Are you, assuming you haven't studied ahead or something, are you in the same boat? You're like, now what to do? Well, again, my only thought is I guess I'll just have to keep going. Like, I'm going to erase this, but now I might try, let W equal U minus 16, and maybe that will get me out of the woods, right? That's the only thing I can think to do. But
Can
let
I
me
give a
show you-
suggestion?
Yeah, go ahead.
Previously, one of the problems we set U to what would be the best option per se. What if you did the same here? Like you set U to what would be the best option for you to be so you could solve it?
Yeah, and that's exactly the point of this. This problem is not easy unless you make a very surprising substitution. Surprising enough that the book and calculus books devote an entire chapter to it. And why it is, and maybe this is where you're going with this, Eve, is, let me rewrite this down below. A better option, to Eve's point, a better option for you. And this is a fix or a trick that only works in very defined circumstances. And the defined circumstance is this. Notice that looks like the Pythagorean theorem down there. You agree with that? In other words, hey, this is kind of a hint that I could kind of look at this as right triangles. This does not work very often. If that was x cubed plus 16, doesn't work. So you're going to be given in 8.4 a very contrived set of problems for which this trick kind of works. And in some respects, to me, that makes it kind of useless in the sense that it's very unusual to ever need this tool in the real world. Although I may assign an extra credit in this section where you try to find the surface area of the torus formula. And in doing that, you need this exact technique right here, which is really cool. And the cool thing about that is in the end result is you actually get an algebra formula for the surface area of a torus, and you never have to do it again. Like calculus is over. For the rest of history, you now have this formula that you can give to people to find the surface area of a torus, and they don't have to invent all of this craziness. And so acting, it's not always, there's a time for this that's really cool. Anyway, can you draw the right triangle for which x squared plus 16 would work? And by the way, we kind of did this before. We did this a little bit before, which is I think where Eve was going with this. In other words, if that had been x squared plus 1, do you remember how the integral of 1 over x squared plus 1 was the arctangent of x? Remember that one? This looks a little like that. And when we actually could make a substitution that would get that done. But I'm just showing you a deeper way of thinking about it today. So if I did Pythagorean theorem on this, the fact that it's x squared plus 16 would mean x would be one of these and 4 would be the other one. It doesn't matter which one is which. What I'm going to show you today is how to not have to look at your note sheet. This is where inverse tangent came from in the first place. You don't have to look at a note sheet to say, oh, doesn't that look kind of like inverse tangent? You don't even have to look at it. You can just say, hey, that looks like Pythagorean theorem, and that would be a right triangle. And for what it's worth, I could throw an angle in here wherever I want. Like maybe, I don't know, maybe I'll throw it up here. And I could also figure out the length of this other hypotenuse side. I could find a bunch of stuff about this now. I could draw that right triangle. Well, would you agree in this right triangle that based on what I just wrote, the tangent of theta is x over 4? If I'd put theta in the other spot, it would have been the tangent of theta is 4 over x. That's fine too. That's your substitution right there. That's the substitution that's going to make this work out. So if you let x be, very surprisingly, if you let x be replaced with, well, 4 tangent of theta. Again, doesn't that look like, who would have thought of that? We tried letting u be x squared plus 16 and it led to a dead end. But if we replaced x with 4 tangent of theta, because that looks like a right triangle, beautiful things will happen. It's a very surprising substitution. Again, very much from left field. Would you agree with that? It's like, what? Where in the world? Why would you do that? Watch what happens if we make that choice. Okay. Let's see. I guess that would be the integral of 4 tangent of theta, but that is squared since x is squared, and so that's fine. There's a 5 up here, but then we got to get rid of that dx, right? So if I take the derivative, dx is equal to 4. The derivative of tangent of theta is secant squared of theta d theta. Notice I didn't have to resolve this. Like, that's what dx is equal to. Now, again, your gut reaction to this should be, this is not a good idea. This is not going to work. This got way uglier, and now it just got even uglier because now I've got secant squared theta d theta. Again, would you agree that I could check this on the calculator, but success. It's all thetas, right? But is it easier? It doesn't look like it. But watch what happens if we keep going here. So let's see, I guess I could multiply, since this is a fraction, I could multiply straight across. So I have 20 secant squared of theta on top. And if I multiply the bottom out, I've got 16 tangent squared theta plus 16. To me, that doesn't look any better. That looks terrible. This does not look like it works at all. However, perhaps the first clue that it will actually go somewhere is, notice what happens if you take that 16 out. Do you see anything now that suddenly looks promising? Whoa, you might say. I happen to know that 1 plus the tangent squared of theta is equal to the secant squared of theta. Bam, those are gone. Whoa, yeah, I guess it is easier. Wasn't that ingenious again? Like, who thinks of this? Who came up with this idea? We were truly at a dead end with that problem just because I took the x off the top. But when Pythagorean theorem is involved, brilliant. So integrals are tricky. Okay, well, let's finish. Let's see, 20 over 16, they both divide by 4, that's 5/4 d theta. So all that means is the constant number 5/4 grows a theta, right? So there's the answer. Except for there was never a theta in this problem. I need to get x back into it, right? So what is theta equal to? Remember, we let x be equal to, what do we let x be equal to? 4 tangent of theta. Or I'll look back here. That's probably even easier. What do you have to do? Because we don't have tangent of theta, we have theta. So don't you have to take the inverse tangent? Hey, that's where that formula came from before. We made that at one time for ourselves. That did look like inverse tangent, which I have a feeling was where Eve was going with this. But I noticed I didn't have to memorize anything. Like, I just made it myself. So theta is the inverse tangent of x over 4. So just so that it looks reasonable in the notes. So the answer is 5/4 inverse tangent of x over 4 plus c. Now you try this out really quick just to check your work. A minute ago, we knew the right answer to this question, did we not? If we evaluated it from 5 to 1, we know the answer is 0.8138. So to check our work, just to make sure, let's do that. So if you take 5/4 arctangent of x over 4 and you evaluated it 5 and 1, notice those are x's and we chose x to be 5 and x to be 1. Do you question mark get 0.8138? Be in radian mode in your calculator, type that in. Five-fourths, which is 1.25. 1.25 times the second tangent of 5/4. I got 1.12. And then I'm going to go back and put 1 in. I got 0.32. (1.12) minus 0.32, 0.8. Cool. Yeah, worked. Should have probably carried those out to more decimal places. Maybe I'll write, just so it looks a little better in the notes, 0.32, I rounded, it was really 0.316. So when I subtract it correctly to 3 decimal places, I get 0.814. So now it's a little more obviously equal. That's pretty cool. So you're looking for Pythagorean theorem. Now, again, fortunately, these problems are partialed out very carefully, like you're only going to see these in section 8.4. If I give you a random problem, like I could on a final, and say nothing about it, just say take the integral, does it make sense? Like, well, it could be trig substitution. It could be, well, what we tried at the start, let's let u be equal to x squared plus 16. Like you could burn 2 hours on this and never arrive at sort of the correct choice. Or maybe you do arrive at the correct choice, but you make an algebra mistake or something. Like this is hard. This takes practice, and we don't want to be this good. You just want to play with this stuff and kind of understand, hey, this is a set of tools, but you can see you're not going to need to do this practically. There's applications to integrals, but in a practical sense, people are not taking integrals like this. If they need to know, as we did here, the answer to that green integral, Desmos will tell you, let's get on with it, build the bridge. I'll set this one up and we'll finish it tomorrow, perhaps. Let me see where we go here. Maybe we'll have time. Another example. What if I asked you for the integral of 25 minus 4x squared? As I said before, that looks like substitution. Let u equals 25 minus 4x squared. But unless there was an x sitting out front for that derivative of x squared to cancel, this problem is not going to work. But again, do you see Pythagorean theorem? Can you draw a right triangle that produces what I just showed right there? Try that really quick. Notice there's even a square root in this one. But notice there's a minus sign, not a plus sign. So you got to be a little more careful about where they go on the right triangle. Pythag. Pythag to the rescue. Again, if that's 4x cubed, game over. Doesn't work. Maybe that one's impossible. I'm not sure. Because it's a minus problem, not plus, and you've squared things, there's no question that the 5 goes on the hypotenuse. 5 squared is 25, and you'd be subtracting that from one of the other two sides. So 5 is the hypotenuse for sure. 4x squared used to be 2x before it was squared. And so that could go more than one place. I'm going to put it here. So would you agree that triangle would produce that Pythagorean theorem that we see up there? So the normal substitution you would pick u equals 25 minus 4x squared won't work. But what will work? If I come over here to this right triangle and I throw that angle in there, and then I note that, and this isn't the only way to write this, I could put the angle up here, and then this would be a sine problem, but I just chose to put it down here. And so that would be cosine of x equals, no, I'm sorry, the cosine of theta. The angle is theta. Cosine of theta is adjacent over hypotenuse. Again, I'm not going to do it, but if you'd put theta up here, then you would have said the tangent of theta is 2x over 5. That would be fine too. There's your substitution. 25 minus 4x squared won't work. This will work. Amazing. Brilliant. Wow. Notice this isn't a typical substitution where you say let u be something. I don't even know how to write this. Should I just write it like that? Should I solve for x? Should I say x equals 5 cosine of theta divided by 2? Let's go a little further. We might have time to finish this. Would you agree that the original problem could be thought of as being this, 25 minus, and I could even write that as 2x squared, and I could write it as 5 squared as well. But the reason I did that is because, hey, this isn't too hard to solve for 2x, and 2x equals 5 cosine of theta. So now I can put 5 cosine of theta right there. Like that's how I can get it into the problem. So you could have solved it completely for x. But do you see the brilliance? Do you see what's happening to this then? Do you see? The problem is we have the square root of junk minus junk, but watch what this accomplishes. Now we have the square root of 25 minus 5 cosine squared. That'd be 25 cosine squared. Do you see what's happening to that? What's happening is exactly what happened in the last problem. Now I can take 25 out of both of them. What's left behind is 1 minus cosine squared. Hey, 1 minus cosine squared can be rewritten as sine squared. Now there's no minus sign, and I can take the square root of sine squared, and that's sine. And so that's where this is going. We'll slow down and get there. But notice you're not done. You still have to get rid of the dx in this problem. What is dx equal to? The derivative of, let's see, where am I going to take the derivative of this? I think I'll do it right here. So the derivative of 2x is 2 dx. The derivative of 5 cosine of theta is negative 5 sine of theta, d theta. So that means dx is equal to negative 5 halves sine of theta, d theta. Notice I'm very careful to replace everything. dx is really ugly. And so again, my first instinct is just like the last problem, which is this is not better. This is terrible. I'm out in the forest. I quit. I'm going to go try something else. That's my instinct. But as I said, watch what happens to this. But this 25 comes out of both of those terms. So that's why it's so important to end up with 25, because now I have just 1 minus cosine squared. And you should look at that and say, oh man, that's rad. That's just the sine of theta squared. So that all I have underneath this radical sign now is a 25 and a sine of squared theta, which means I can actually take the square root of that. That's amazing. That's totally cool. And I still have all this junk coming along for the ride. So the square root of 25 is 5. The square root of sine squared is sine. So I have 5 sine of theta times negative 5 halves sine of theta. Notice it's not as good as last time. The signs don't cancel here. They don't cancel, and I just have a constant. But I have, if I take the constants outside, 25 halves sine squared of theta d theta. I can actually take that integral. It's not easy. We did that yesterday, actually. That wasn't easy. But miraculously, that surprising, crazy substitution actually got me to a place that I can actually solve. Sine squared theta. Oh yeah, that was the cool shortcut. That was the cool substitution to make from yesterday. Sine squared is kind of ugly, but if I replace it with 1 minus cosine of 2 theta, then it's not squared anymore. Yesterday, we also split sine and sine into 2 parts and used integration by parts and got it to work too, which again, I was surprised at, but this is the easiest substitution to make. Because sine squared of theta is a function inside of a function. It's a sine of theta and squared. That is not simple, but this will simplify it. So this is a substitution, but it is not changing letters. Do you notice that I made my life a little easier by pulling that 2 out front with this other 2 so that I don't have a fraction? Now I can take the integral of 1 with respect to theta, which is theta. I can take the integral of cosine, which is negative sine, which actually turns that into a positive. So the derivative, just to check my work, if I take the derivative of the sine of 2 theta, it's the cosine of 2 theta, but then times 2. And so I would need to divide by the derivative of 2 theta down here. Again, that's kind of a substitution problem. Done. Well, not done, because remember there was never any thetas in this problem. I need x's back. So what was we said that 2x was equal to the 5 cosine of theta. That was our translation between the two worlds. I'm also thinking back to my right triangle that started all of this, where this was theta. And this side over here was the 25 minus 4x squared. So what is theta equal to? It's equal to the inverse cosine of 2x over 5. Thanks to this statement, isn't this another way to write this? Is 2x over 5 equals cosine of theta. So to solve for theta, don't I have to take the inverse cosine? But what about the sine of 2 theta? I don't have two angles. Does that jump out to you in your memory that that's an identity? Look it up on your sheet, but the sine of 2 theta is equal to 2 sine of theta cosine of theta. So if I replace that, notice it's half times 2. This whole statement then just becomes the sine of theta times the cosine of theta. Cool. The cosine of theta is 2x over 5. The sine of theta I can get from this right triangle over here. The sine of theta is opposite over hypotenuse, which is the square root of 25 minus 4x squared over 5. There. Wow. That's crazy. It's hard to believe that's the answer, isn't it? The integral, the original problem was the integral of square root of 25 minus 4x squared, and that's the answer to it? Wow, you gotta be kidding me. Study that example, because that's pretty challenging in every respect. Like, you had to know all these identities, you had to draw right triangles, and there's a lot of stuff to consider there. I need to shut up. So come with questions tomorrow. We'll spend a little bit more time with this concept, because obviously this is going to take some practice. We'll go from there.
I had a little question about the one we did beforehand.
Sure.
I just tried it a different way, I guess.
Mm-hmm.
And then I wanted to see the hole in my logic, but I did, it's the 5 over x squared plus, or no, 5 over x squared plus 16 one, the one before this.
Yep.
I did it so that I just rewrote it as x plus 4 squared on the bottom, like parenthesis x plus 4 squared.
Okay, we'll stop right there, because that's where you went wrong right there. In other words, you rewrote this like this, right?
I think so, yeah.
That's not true. If you multiply out x plus 4 squared, you don't get x squared plus 16. What do you get?
Oh, you get a 2x. Never mind.
Yeah. Now I want to compliment you. Like, that's a great idea. Like, if that had worked, notice now you could let u be x plus 4, which is probably what you did, and then wonderful things happened. That would have worked.
Yeah, but then I checked it with the integral and it was always wrong. I guess, yeah, no, that doesn't work.
Yeah. And that's the kind of thing that's why these problems are so hard, because you have to know everything you've ever known, and that's a pretty honest mistake that you made right there. And so that's why I'm really glad that you asked it, because it's probably not just you that's benefiting from that. If it was possible to write x squared plus 16 as x plus 4 squared, that would have been an easy approach here, way easier, but it just is not true. Awesome point.
I got you. Thank you.
Keep going. Who else has questions?
Can I check my answers to the quiz?
Yeah. Let me find that thing. Right here somewhere. Found it.
Okay, so for question 1, I got negative 0.6696. Is that correct? Even though it's a negative?
Yep.
That would just mean it's below the x-axis, right?
Yeah. Some
Okay.
total. Like, it could have some above and some below, but that's basically saying there's slightly more below than there is above. Or the whole thing is below and it just
Okay.
big. And you do know you can check that yourself, right? Like, you can graph that yourself and know that decimal answer is right. You don't have to ask me that. I don't care if you do, but I'm just saying on a test, you
Okay,
can
yeah.
graph that and check that, right? Which on the test, that's one of the reasons why I might ask you to do what I did here, not just find the integral of x minus 4 over 2x plus 5, but even include the 6 and 2, because that helps you check your work.
Okay. Mhm.
Good job. Keep going if you have more.
So for the next one, I got 11.296.
Also true.
Negative 0.543.
Yep. Also
Then
true.
41.1986.
Also true.
And then 4/3.
Also true.
And 0.2146.
That's also true.
Okay, great.
Gabriella.
Thank you.
Nice job.
Wait, I'm confused. Did she say for problem 1 she got negative 0.6696?
Negative 0.06696.
Okay, I was like, because I don't have that. I have like negative 0.067 because I rounded up.
Yep.
I was like, oh my gosh, where is this extra 0.6 coming from? All right, cool. I'll see you tomorrow.
See you tomorrow.
I had a question about the extra credit on the last project.
Yes.
I goofed on the 650 pounds.
Mm-hmm.
How would I set that up in the equation?
Yeah, so the problem is on the footing. This
Yeah, I had the
distance
same
is
problem.
16.
And I redid it. And I got 15.961 for the X.
I think that's too small. Off the top of my head, I'll have to look at my notes in
Okay.
a second, but let's keep playing with this. So the problem is this distance right here is X now. Does that make sense?
Mm-hmm.
So 650 is not true anymore, because 650 was based on this distance right here being, I think, 42 inches long. It's not 42 inches long anymore. It's X plus 24 inches long now.
Oh, okay. So just X plus 24.
Exactly. So that's the one exception. Like all the other shapes did not change. This wall right here did not change. It's the same exact size that it was before. But now the volume of that footing down there it's height, which was 1 foot, times, we were thinking of this as a 1 foot slice, so its depth is 1 foot times its area here, but its area there is x plus 24, at least if you think of that in inches. And that is a problem that that's inches, because you can't get volume by going foot times inches. And so you don't get 650, you actually get in a formula. You're going to get a formula for its weight. And then it's concentrated in the middle of this, which used to be 21 inches, but now it's not 42 inches long anymore. Or
So I have to
52.
redo the equation to find my new.
Yeah, so you have a really kind of an ugly equation for the footing, unfortunately, and that makes your math really cool, but a little bit more time consuming.
Don't you, when you multiply it, do you, you multiply 150 by x plus 24? Do you divide x plus 24 by 12 to make it feet?
That's right, because it's 150 pounds per cubic foot, which means this needs to be cubic feet. And it won't be cubic feet unless you, as you said, divide this by 12 to make that feet. So doing that, this is now feet. So it's feet times feet times feet. That's now cubic feet. So you get a formula instead of 650. And then your distance to the toe is that distance right there. But that distance is the middle of this block. It's not 26 anymore like it used to be, since this block used to be 52. I said 42 before. Used to be 52 inches long, but now it's x plus 24 long. So, you know, where's the middle of that? That distance is in the middle of an equation, not the middle of a number now. So it makes the footing really messy, but beautiful.
All right. Well, I'll look at that.
Did you see whatever you must have done wrong, April?
No, I can't find it.
Did you do what I said here? Like, is that, I can't remember what comments I made on yours. And
Well, so I redid it after you made the comment on it,
got it.
and I did the 50 times 24 plus x over 12. And then I replaced that with the 650 for my calculations.
What went here? Because all of this is just pounds now. This is your force. But what's your distance?
My distance is 24 plus x over 12
Not
for
true.
the footing. What?
That's not true.
Oh, it's not?
Think about that a little bit more. You're right. The overall distance across here is not 52. Now it's x plus 24.
Okay.
But isn't that weight concentrated in the middle of that? So isn't this distance right here half that size?
I don't know what you mean.
You just said x plus 24 over 12 is your distance, but isn't this whole distance right here x plus 24 over 12 feet? I mean, that's if you want it to be in feet. In other words, you made the distance all the way to here as though the force of the concrete is acting at the end of the concrete, not in the middle.
So what I want it to be x plus 4?
X plus 4. Why 4?
Because that's in the middle of the beam.
Well, remember, this distance here is not 16. In other words, the 8 is not in the middle of this.
Oh. Okay, that makes it harder.
Let's get it before you get off though. Let's make sure it's right before you get off. So if this is the top of the footing and you agree that the distance up there is either x plus 24 inches or x plus 24 over 12 feet, whatever way you want to call it, then isn't the force right in the center of that?
Do I want 1/2 of that then?
Exactly. That's what you did before. Didn't you take 52 and cut it in half and say 26? It's no different.
So would it be easiest to just divide it by 6 then?
Which one are you talking about? The x plus 24 or the x plus 24 over 12?
X plus 24 over 12 if I divide it by 6 instead of 12.
Yeah, but if you divide that by 2, you don't get 6. You just made it 2 times bigger than it was by making 12 6, not 2 times
Oh.
smaller.
24.
There you go.
Okay.
And you do want it to be feet because the force needs to be in pounds and the distance needs to be in feet. So you do want this equation. That's exactly right. So that's right. It'll be x plus 24 over 24.
Okay. Thank you.
Yeah, think about that. Good questions.
See you later. Bye.
See you later. Dominic, you there? Any questions for me? All right, later.